Welcome everybody to this webinar on input filter magic is what I'm calling it, and we'll find out later on why that particular title was chosen. So lots of people in the room here, coming up on about 500 people, so it's a big event that we're running. Hold on a sec, I'm just sorting out my 4 screens here. So this is a seminar that I tried to give about 3 years ago at the APEC conference, and then COVID canceled the APEC conference for us, so I didn't do it. And here we are 3 years later on. I was supposed to do this February 2nd, and then COVID came to get me, so we didn't do it again on time that time. But both of these delays actually have been really good, because delaying from APEC has given me 3 more years to think about the project from time to time. And then the last 3 weeks, I've added a huge amount of material in there that I didn't anticipate to add. So it's all been good to do that. Okay, so let's get started. I'm not going to introduce myself. I think you all know who I am at this point. Go to ridleyengineering.com if you want to see my bio and the products and things that we do in this industry. But let's get right into the topic of input filters. So here are the big players then that become part of this presentation. And this is a topic that's as old as power electronics itself. And Dr. Middlebrook presented originally the problem of input filters interacting with power supplies. And that was back in 1976 when that was published. So obviously he'd been thinking about it for a few years before that. And I was fortunate enough to meet Dr. Middlebrook in, I think, 1982 was when I met him. I went to his course. He was teaching with Dr. Chook, and the one thing that struck me in that course was it wasn't about power electronics. This is something that not too many people know about Dr. Middlebrook, is that power electronics was not really his thing. He was very much into circuit analysis, analog circuit analysis, and he was the main thrust of his work was impedance interactions, the extra element theorem, where if you've done the hard analysis on a circuit and then somebody changes it on you, do you have to start all over again? Or can you look at some impedances of nodes of the network and then use what you've already done to say, okay, nothing's really changed, and let's move on with what we've got. So that was really the theme throughout his career. And the reason he went strongly into power electronics is almost the only field left that does analog analysis anymore. So the funding is there for power electronics, and the funding is not so much there for just generalized circuit theory. So he started the big issue with input filters that we're going to talk about here. But I encourage you to read the rest of his work on the extra element theorem. That's really fascinating. And the next big player in this was Dr. Kelkar at Virginia Tech, who was the first one that I saw who tried to break out of just thinking of converters and saying, okay, if we got a converter and a filter, maybe we can control things that are not just the converter. We can to the filter and change the filter to do the control. And he presented this work in his dissertation and in several papers later on that we'll talk about. So some things didn't quite work out there, but the real contributors in this field are the people who try something new, even if it has some mistakes in it. It's better than just sticking with the old. And when it comes to this topic of input filters, nothing really has happened in 50 years that's been published. Everybody's just saying, well, you got to damp the filter and keep the impedance low. So he tried to do something different. Then we have Dr. Vlatko Vlatkovic. He was a PhD student at Virginia Tech, and he was working with a couple of other people, including Dr. Bo Cho, who found the issue with Dr. Kelkar's solution that we're going to talk about during this presentation. I think Dr. Vlatko is now, he's like Director of Research at General Electric. And we have Dr. Vorparian. Good friend of mine for many decades, and he's the best analytical mind in power electronics. And without his PWM switch model, none of the work here would have happened in this presentation. And he, of course, was a student of Dr. Middlebrook, and he continued on Dr. Middlebrook's work of extra element theory analyzing circuits kind of by inspection without doing things the hard way. So I do encourage you to get his book as well. And one more person I want to mention is Art Nace, who is actually, on this call as an organizer. You can ask him questions directly. He's an aerospace engineer and programmer that's been around much longer than I have in power converters. And he did all the programming and automated LT Spice models for us from Ridley Works. And he's also our longest term user of Ridley Works. So if you have questions about using that and what it's done for him and his projects, you can talk to Art. So thanks, Art, for all your contributions there. And he's put in a huge amount on this input filter issue because we tried a lot of weird things over the last 3 years to see what we could do. So basics. This is the stuff that everybody knows or should know, and this is the stuff that just gets published again and again. Another webinar, another presentation, everybody talking about input filter measurement. Again, it hasn't changed since 1976. And the first paper was from Dr. Middlebrook. So I took this figure straight out of his figure 1 in his 1976 paper. And by the way, you can't find that paper in the IEEE Transactions anywhere. I don't know why, but the IEEE hasn't uploaded it. But if you do click on the link that's here in the bottom corner of the page, the input filter Middlebrook link, you will find that paper on our website because it subsequently got released by the British Library. So that paper is finally available for everybody to go get. So what Dr. Middlebrook did was he identified a switching converter. Here we just see a buck converter. Early days of power electronics, so it's a bipolar transistor, a diode. There's a regulated output. There's a feedback loop around it all with an amplifier and a modulator. And he started looking at the source impedance, that's the output impedance of the input filter, versus the input impedance of the switch mode converter. And his famous paper talked about what those relative amplitudes should be in order to keep your system stable. Now remember, this is all part of his bigger theme. He'd analyzed the buck converter, done that. Dr. Chuk was part of that with state space averaging as well. Found all the transfer functions, and then you come along with another filter and you really don't want to repeat the analysis with this higher order system. So he said, okay, let's look at these impedances. If we can say one impedance is much lower than the other, then our transfer functions are still going to be valid. So he's trying to preserve the value of the analysis that's done, not to make it too much more complicated, which is a very, very powerful thing in the world of analyzing circuits, especially as you start getting to these really big systems we have now with multiple converters in parallel, multiple filters, input and output. There's no way to analyze. So you have to use this impedance approach to see whether systems are going to work properly. So this is Middlebrook's original problem description. And what I'm going to talk about first are just the practical considerations for system testing and the necessary measurements. We've been in the measurement field for, I started making measurements on power converters back in 1980. So I think I've used every frequency response analyzer that's ever been on the market. And I just measure everything. So sometimes I assume that everybody knows the procedure for input filters, and it turns out talking to people that they really don't. They read the original paper and they make it much harder than they need to for quantifying the input filter. And one thing I have to apologize here during this presentation, by the way, is this is a 3-hour presentation squeezed into 1 hour. We asked people how long they wanted webinars to be, and they all came out. We got 1 hour. We don't really have time for longer than that. So there'll be a lot of information coming at you, and then depending on the feedback, we may break this into pieces and put it into information on our website later on. But here's Middlebrook's filter again, and now let's draw this in terms of blocks. So we've got the input filter here, which is not necessarily restricted to just an LC. It could be multiple L's and C's in there. And then you've got the switching power supply. Now it's very important to realize this switching power supply is only the switching block in here. In a couple of slides, we're going to see why that's important. So now we're looking at the input impedance of the power supply, output impedance of the source. If this output impedance is much lower than the input impedance, we know that they're not going to interact with each other in a negative way. How do you make these measurements? Well, it's a tough measurement to make because you have to break into the AC bus, the positive of the AC bus, and inject a sinusoidal signal. And this is really hard to do and get a good signal in there, especially as power levels go up. Remember now, you're also injecting into here where you may have capacitances all over the place that's going to severely load this AC injection point. But this is the concept of doing it that you can certainly do in LT Spice or any simulation package. If you want to do it, so you inject the signal here, and we'll show you an injector in just a moment, and then you measure the ratio of the voltage across the input filter to the current out of the input filter. That gives you the output impedance of the input filter. Over here on the switching power supply, you measure the ratio of the resistance, of the voltage, sorry, at the input to the current flowing into the terminal. So you're just making an impedance measurement with one injection point, and that looks simple enough. Here's a line injector that we make to do this. It goes up to 80 volts on the input. You can run 10 amps through it, and it will perturb this input rail. It's got an active device in it, but it's not a high power active amplifier, which is what you would need if you really wanted to drive the system hard. And that would be a very, very demanding amplifier to build because you'd have to have it carry the full DC current of your power system, the full DC voltage, which may be 400 volts, 800 volts, whatever it is, and it's got to modulate into some low impedances. So injecting into this part of the circuit is difficult, and the measurements in general are not very satisfactory. You don't see a lot of published measurements on these because it is hard to get a good signal in there and then measure the signal when you're done, because the impedances can be quite low and the signals can get quite small. Okay, so it's the most difficult of all the transfer functions measurements to make. Some people get intimidated by loop gains. Loop gains are actually the easiest measurement of all to make. You should always do your loop gain. Impedances and injecting into the line, power supply rejection ratio, they're the most difficult to make. So if you can avoid it, you should avoid it. And when it comes to the input filter, you don't actually need to make this measurement to make sure that you've satisfied Middlebrook's criteria. And if you click on this block here, you can link to our little injector, by the way, in the PDFs that you have. So, and even if you do measure it successfully, so if you put our line injector here and you make these measurements, it's probably the wrong measurement. This is something that gets overlooked time and time again. People end up with the wrong conclusions about instability. And even worse than that, they can end up with some very poor filter designs and very poor system designs that are much bigger than they need to be because you're not actually measuring the right quantity. And where it goes wrong is that you may be purchasing a power supply and then you're putting an input filter in front of it. You're defining your Z in and Z out. But any filters that exist inside the power supply, and you're going to have at least some bypass caps to take the high frequency current, they're not part of Middlebrook's definition of the power supply. They're part of Middlebrook's definition of the filter. So the correct measurement to make to satisfy Middlebrook, you should take this cap on the input of this supply here, doesn't matter if it's a flyback or anything, and the filter cap goes into the filter. And then the only thing that's left here is the flyback power supply, or the buck power supply, or full bridge, whatever you're using. So this is the measurement you should make for the filter, including all the filter components that live inside that power supply block that you may not have access to. But if you don't apply the measurements this way, then you're going to come to the wrong conclusions about the stability of the system. So not too many people talk about this. But I do see a lot of power supplies measured wrong where they've got lots of input cap here. And that, of course, lowers the impedance. It makes the impedance interaction look like it's much worse than it really is. But you take the cap, you move it to the filter. That's where you do your analysis. Okay, so my approach is don't even bother measuring the input impedance to the power supply, because you can't actually measure just the switching stage without some filtering on. And even if you could measure it, the measurements would be very noisy, but there's not a lot of reason to measure it because it follows along with the theory very well. And we'll see what the deviation is a little bit further on. But you should measure the output impedance of the input filter. Okay, Z in of the power supply is very easy to approximate. Z out of the filter is pretty complex because you don't have a good model of what's inside the filter, what's doing all the damping, what cable impedances are, what upstream transformer impedances are. So for me, the one essential measurement is this one, where you measure the filter output impedance. Make sure you short circuit the input of the filter. If you don't short circuit it, you're not making the right measurement. And if I can do this, take my little camera here, I can show you a little filter measurement here. Let's see. There's our AP. And we've got a filter here. And the measurement includes all the impedance of the line cord, and then you short the plug right there. Okay, so it's very important to make sure you measure everything there, including the line cord, including the distribution cable that you have. This gets really important as power levels go up. If you're doing 100 kilowatt type converters, some of you already know, the impedance of the source, the impedance of the line, the impedance of the battery that's feeding you can interact with your power converter in the same way as an input filter. So you make the measurements, that way, including all those impedances. And just to get away from PowerPoint for a moment, here's a measurement that's going on for you. It's okay, that's measuring nothing. So sweeping a filter is really it's a 3-second job here once you've got the right analyzer to do it. So you can see here, this is an input filter. It's not just an LC, it's got an L here, and then it's got another LC here. So it's at least a 4th order filter. This is just a canned filter that you would buy from a vendor of input filters. And they've done a pretty good job of damping the filter. You don't see sharp spikes here on the resonances. So we're looking for these impedances to see how they're going to interact with the power supply. So that's the one measurement that you need to make. And then the next measurement would be the input impedance of the power supply, but you don't need to. You just calculate minus V squared over P. So this is your input line to the power supply. That's the input voltage. P is the power level. If you want to go a little more sophisticated, you include the efficiency as well. And then you want to make sure that that peaking from the filter is not going to crash into this red line here, which is the the negative input impedance of the converter. Okay. So only one measurement really to make is blue and the red. Now, for some of you that are in aerospace and system design, this practical comment about the only thing to measure is the filter is probably not going to help you because it might be part of your spec to make all these measurements. But they are tough to do. We can help you do it if you have our test equipment for doing that. But, two things then, you've got to be measuring the right place in the system and you got to make clean measurements. But calculation is good enough for those that don't have the input impedance as part of their spec. So you can see here we have a critical case showing up where the peaking of the filter is just touching the red line of the input impedance of the power converter. That's where we're going to expect to see some problems with interaction of the filter and the power supply. So here's the rules. Make sure you identify what's the filter, what's the power supply. do not include the filter components in the switching power supply. Make sure you move those into the filter. Don't include those in the power supply input impedance. So you put a short circuit on the input to the filter, okay, because you can have a voltage source there in the real world. So you put a short circuit there. Otherwise, you get a totally different transfer function. And then you measure the unpowered filter impedance with the device, such as the AP or the Ridley box or whatever you want to use for that. And then you plot the calculated input impedance of the power converter on the same graph. Make sure there's good separation between the two. And then Middlebrook always used to point this out. Make sure the filter is well damped. Even if they don't talk to each other, they're not that close to each other, the ringing on the output of the filter is going to cut into your dynamic range. So even if you've got well separated, don't leave a really undamped filter in the system. Otherwise, you're going to lose dynamic range on the converter. Okay. All right, so that's the essentials. If you're somebody, you're just trying to build a power system, you want to make sure it's not going to oscillate and do due diligence. That's all you need to do. So it's really, you know, probably a half-hour job to figure out what to do there and to make sure things are not going to interact, and then you're done. But Middlebrook's paper went quite a bit deeper than that. And the first thing, I'm not going to run this LT Spice model, but we build all our LT Spice models directly out of Ridley Works usually. It really speeds up. So this is a voltage mode control switch model from Volparian. Here we're injecting a signal into the rail, and now we're going to measure the actual input impedance versus just this approximation of V squared over P. So we run that simulation in LT Spice. And you can see here, if you made the approximation that your input impedance is minus V squared over P, you would get this blue line. And then when you measure the input impedance of the actual converter with the loop on it, you can see it's equal to that blue line up to the crossover of the loop, and then it rises. So it's actually rising with the impedance of the inductor of the circuit. So you can see that assuming the blue line is our input impedance is a conservative approach. That's actually a lower value than the actual impedance, which is rising after the loop gain. So if you just assume it's constant, it's doing a more conservative design here. Okay. I see some questions there. I'll take a couple of minutes in a moment just to answer the questions after I'm through this little part. So there's that. And then Middlebrook talked about, in his paper, he went a little bit more complicated. He said, well, not only do you have to have the output impedance of the filter less than the input impedance of the converter when its loop is closed, so that's that flat line. He said, if you truly don't want to interact in the transfer functions, then the open loop, the output impedance of the filter mustn't cross over the open loop input impedance. I don't know anybody that adheres to this, because you've got a block that's a power supply. People don't usually even know what the open loop input impedance is. But he was quite right. If you don't want transfer functions to change, you don't let this red curve crash into the green curve. Okay, but that was just going in deeper, that you really don't have to do that from a practical point of view. But what he was getting at was that now if we take a power converter here, so here's a buck converter, it's got an LC filter in front, and it's a very undamped. There's only 6 milliohms in series with the inductor, 3 milliohms in series with the cap, and then we're running a loop sweep on this on the system. So let's look at first some impedances. So here's this system, and we're going to vary the resistance of the cap here. So here it is with a big damping resistor, 200 milliohms. Here it is with a 30 milliohm resistor. Now you can see the blue line is reaching up to the red line. And then we put in 3 milliohms, and you can see them crossing over there. So we know we're going to have problems with this last case in the system. So now we're going to take that LC filter. So here's a buck converter loop with no filter in it. So it's -1 slope, double pole, -1 slope, nothing going on in the region of the filter because we haven't applied the filter in yet. Now we put in a well-damped filter where the two curves are separated. And there's no stability issue, but you can see the effect on the transfer function. There's a little blip here in the 5 kilohertz region. So that's where Middlebrook was talking about those, the open loop input impedance talking to the output impedance of the filter. It's changing the transfer functions, but it's not unstable. We go one more step. Now we're at 30 milliohms where those lines are just touching each other. And what we've got is this big glitch in the transfer function here. And the glitch turns out to be left half plane zeros, but very high Q. So there's a big spike there in the phase, and you see a dip and a spike there. And then it goes on, you know, being a -1 slope afterwards, but there's high Q left half plane zeros in there. It's still stable. And then here's the step where we've gone to 3 milliohms. It's very undamped. And now these left half plane zeros become right half plane zeros. And you're looking around the loop here, and then suddenly, boom, it drops down 180 degrees at that point. 180? Yeah, it's 180 degrees at that point. So the zeros have moved from the left half plane to the right half plane. Now we're going to have stability issues in here. Okay. So that's what's going on as we're letting those two curves interact. By the way, separation, good separation for me, it would be 10 dB. But for Middlebrook, he said also, well, of course you've got to damp it as well. So that would be good separation. The input impedance, of course, is negative, but we're plotting the magnitude, so it doesn't matter whether it's negative or positive. So that answers a couple of your questions there. All right. And here we have a simulation of the system. And you can see it turns on, that's ringing. It just gets bigger and bigger and bigger with time. So we're oscillating at around the resonant frequency of that input filter. And there's really nothing at this point we can do about it except for damping the filter, lowering the impedance, and then make this go away. So this is the oscillation we're trying to avoid. Now, why are we still talking about this after 50 years? Well, in the old days, filters used to be, you know, they had big bulk capacitors in them. We weren't trying to minimize the size. We had electrolytic caps, which used to damp things quite nicely. What's going on now is a lot of board mount power, where people are building their own filters. They're using multi-layer ceramics, very low ESR. They're using the best inductors they can use to get the filtering. So this problem of high Q filters and high impedance filters has gotten much worse in recent years, but the problem's always been there. It's always been the same. Okay, so that's part one and part two. Part one, the only measurement you really need to make is the output impedance of the filter. Calculate the input impedance of the power supply, you're done. If you want to go a little deeper, you plot some loop gains and you say, okay, well, this is what's going on. You can see the interaction and you're penetrating a little bit deeper into the system. And then you can see the interaction approaching. You can see the sharper glitch in the transfer function. So you really want to stay away from that region. Now let's look at a really interesting thing that happened in this industry, which is input voltage feed forward. And this was a dissertation by Dr. Kelkar from Virginia Tech. He was just before me there. I think he graduated while I was at Virginia Tech. But he wrote a very, very interesting input filter compensation scheme for switching regulators that were quite prominent in the industry. And what he did, some of you may remember this, or you may see this kind of chip from time to time. For the ramp of a PWM converter, normally it's driven by a current source. So that current source is just set by the reference voltage of the chip. But in input voltage feed forward, the ramp is set by the input voltage. So if you double the input voltage to the converter, you double the slope of the ramp, you halve the duty cycle. So it was called feed forward because immediately when the input voltage goes up, the duty cycle goes down. So there's automatic compensation for changes in the input line. So there were a bunch of chips that came out to take advantage of this. You know, there's still some chips you can buy these days, even modern chips, that look at the input voltage, adjust the height of the ramp according to the input voltage. And it has a really interesting effect. So here we have our buck converter, feedback loop that we're ready to measure, input filter, and then we've got feed forward from the input of the power supply straight through to the duty cycle. Okay, so we're changing the duty cycle immediately. When the input voltage on the filter goes up, the duty cycle immediately cuts down. All right, so that's the way the feed forward is working. And then it has an interesting effect on the loop. So here's the loop with no feed forward in there, and you see that big drop with the right half plane zeros. And then here's the magic loop with feed forward. All of that unpleasantness at the filter resonance just goes away. So when this work was done, this was presented at papers at the High Frequency Power Conversion Conference, and it had fixed the input filter problem. I just made it go away. So it was kind of a magical fix. This was good because sometimes it's you know, costs a lot of power to damp the filter properly. You don't really, you get the filter is what it is. You don't want to have to go change it because you're unstable. But this feed forward technique seems to fix the problem of the filter interacting with the power converter. And then later on, I think in the third series, the third year of publishing the paper on this feed forward, you know, Dr. Kelkar observed that if you do current mode control, it does the exact same thing. So you've got an undamped input filter. The Middlebrook criteria said that, hey, this input filter should be interacting with the power supply. It should be unstable. The curves are crossing over each other, but the loop gain shows nothing. So this current mode loop gain shows plenty of phase margin, up around, crossover here is around 60 degrees of phase margin. And then the voltage mode system also, it's just got plenty of phase margin in it. So feed forward looks like a really good thing to be doing. So that's that one. And then here is the transient simulation of the system with the undamped filter. And let's go run a spice file just to make it more interesting, shall we? So let's see if I can find that. File, open, number 4. Okay, so here's we're using a current mode system now, actually. And we've got this undamped input filter with 3 milliohms in here. And we're going to simulate it for, let's do 10 milliseconds. All right, that's fine. So when we run the simulation and we look at the output voltage, say, okay, well, look, that's really good. It's running. Everything is stable in the system. It's coming down and it's regulating at 12 volts. So the system looked like, yeah, that input filter is really not getting in the way. So far, the loop gain and the, you know, is agreeing with the simulation. There's nothing wrong with the system. Feed forward seems to have fixed the problem. But if we keep on doing our simulation, oh, see that there? We just got a little bit up. Now, actually, it is oscillating. So we put this on our Facebook Power Supply Design Center group recently and said, what's going on here? And people said, well, there's transients, it's large signal, blah, blah, blah. It's like, no, not really. What's going on here is this is the output voltage of the converter. If I were to plot the output voltage of the filter, It's always oscillating. So that was always oscillating, and you couldn't see it until the oscillations got this big. And then suddenly the converter couldn't regulate out that oscillation anymore. Somebody asks, is it peak current mode or average current mode? It doesn't make any difference. It could be peak current mode, it could be average current mode, it could be feed-forward voltage mode control. But this is peak current mode. Okay, some of you are not hearing audio. There's something wrong with your computer because only one person is mentioning that. So here we have an unstable system, but the loop gain said it was stable. The simulation up to 4 milliseconds would agree with that, but after that, you can see clearly this is not a stable system. So what happened in here? Okay, here's the transient simulation. Here it is when we go on for longer, but the loop said it's stable. Why does it go wrong? Okay, when does a loop gain go wrong? And actually, this we put this question on our group 6,000 engineers. Nobody got the answer to this one. Normally, somebody gets the answer. When is it that loop gains don't work and they don't tell you what's going on? Well, we'll answer that question in a moment. But here's the simulation. It's always oscillating. Why can't you see it on the output? Because when you put current mode on a system or you put voltage mode on a system, you get superb rejection of the line. Input voltage goes up, duty cycle goes down. You can't see it on the output. So here you're getting, minus 100, peaks up minus 75 or something dB. That means that oscillation on the input filter is attenuated, almost 10,000 times. So it's not showing up in the loop. So this is what we call an unobservable system. By putting the feed forward on it, you've got rid of the ability to see the oscillation. So the loop can no longer compensate for it. And yet that loop gain model, somebody said the loop gain model doesn't include the dynamics of the input filter. It absolutely does. Here's our loop gain. Okay, the power stage model doesn't need to include it. The loop that we're measuring here includes the filter, but you can't see it. Oops, sorry, I'm not in presentation mode. You can't see it because the line to output rejection is so large. Okay, so this is not a large signal issue, it's a small signal issue. You just can't see it in that transfer function, and that is what we call an unobservable event. In control domain, we have things which are called unobservable. Okay, so that's what we've got going here. Now, when does a Bode plot not work? So this is covered in Bode's original work, but we don't often run into that system in power supplies. So if you look at what's going on here, you've got a -1 slope all the way here. It starts with that, it goes through the peak of the resonant frequency, and then it goes through this blip, but it stays at a -1 slope on both sides. So what's happening in this region here is actually a pair of poles and a pair of zeros almost coincident with each other. And when you pass the stability point, let's see, we get 180 degrees phase drop through this region. And then when we're before the instability point, we don't get that sudden 180 degrees. And what's happened is that we've introduced 2 right half plane zeros into the loop. This is before the feed forward is happening now. So you put the filter on, measured the loop, you saw 2 sharp right half plane zeros in here, very high Q. And then the claim was that feed forward eliminates right half plane zeros. But now we get to some things on what we call feed forward and what we call feedback. So everybody refers to this as feed forward because it's the input to the power supply. In the control domain, feed forward is a gain from a source to the control quantity. So if you sense the input voltage here, which is a source, and you fed it to the duty cycle, that would be feed forward. Anytime you're looking at this quantity here, it's actually a capacitor voltage. So when you're looking at state variable, and feeding that to the duty cycle. It's not feed forward, it's feedback. So control from a state to duty cycle is feedback, not feed forward. Okay, it gets called that because in power supply land we get a little bit sloppy. We're not in general controls people, but feedback is control from a state to the controlling variable. So we actually have feedback in this quote feed forward system here. All right. Why is that important? If you do feed forward, which is what this control scheme was originally called, you can move the zeros of a transfer function. So maybe the thinking was then that these right half plane zeros were getting shifted back to the left half plane by using feed forward. Sounded good because they disappeared in the transfer function. But this is not feed forward. This is a feedback system because it's coming from the capacitor of the filter. And when you do feedback, again, if you're heavy into controls, you know that feedback can only move poles. You can't move zeros with feedback. You can only move poles. So I remember this idea being presented, in the conference every year, and everybody loved this idea because it's great. And every year, Dr. Middlebrook got up. I was there, I saw him do that, and after the third year, he got up and he shook his head. And he said, I've seen this idea presented for the last 3 years at this conference. Something about it really bothers me, but I can't quite put my finger on it. And he just sat down. And then nobody knew what to say. So something bothered him, but he couldn't figure out what it was that bothered him. And everyone was puzzled because everybody else said, hey, this is a great idea. And for 3 years or 2 years in a row, at least, the paper that presented this idea was voted the best paper in the conference. It won the award. I know that. I was there voting for it myself. It was great. So nobody really understood what Middlebrook was not quite getting his finger on. But the answer is, since feedback can only move poles of a transfer function, you can cancel 2 right half plane zeros if you put 2 right half plane poles right on top of them. So the so-called feed forward was putting 2 right half plane poles on top of 2 right half plane zeros and perfectly canceling them in the transfer function. Okay, so that's what Middlebrook couldn't quite put his finger on. Rudy's talking about feedback, feed forward, different things here. Nobody was going back to basic control theory until Dr. Vlakovich, finally dug into it and brought that up. So when does a loop gain not work? A loop gain doesn't work when you have right half plane zeros in your transfer function. Sorry, not right half plane zeros, right half plane poles in your transfer function. So you built a converter, you put feed forward on. When you're measuring the loop, that system has 2 right half plane poles in it. And the rules on a loop gain, if you go from the Bode plot to the Nyquist plot, is that you have to encircle the -1 point as many times as you have right half plane poles. So the system is covered in Bode's theory. People talk about non-minimum phase systems, but right half plane zeros don't really affect it. It still works. A loop gain still works for right half plane zeros. It does not work for right half plane poles. So that's the fundamental problem in the system. So that's the answer to the problem. The loop gain here looks perfect. The simulation oscillates. Nothing to do with large signal, small signal, anything like that. It's just that there's right half plane poles in the transfer function. And then it's not meeting the criteria of encircling the -1 point. You have to encircle it twice if you do the Nyquist plot for this. And clearly, this is not going to do that because its phase is never dropping down that much in there. Okay, so people run into this. You run into it with filters in the system, feed forward control obscures the problem. You can't see it anymore because of the noise rejection. But really what you're doing is creating a right half plane pole system. that's when the loop gain falls apart. Doesn't happen very often because in a power converter, usually everything is passive and you can't have right half plane poles. It does happen for other people. So if you're controlling a helicopter, for example, it's got right half planes poles all over the place, and they have to compensate that properly. They don't do it with loops anymore, but if they did it with loops, they'd have to be encircling the -1 point there. They couldn't just take the straight loop gain and solve this problem. Okay, so this feed forward technique, as it stands, does not work. Okay, and at the time there was a little bit of controversy about that. Well, this person has done this dissertation, but it's good work. It's good work. First person to try and control the filter, great. The fact that it didn't quite work, well, we'll go fix that, and then we'll try to make it work. So we moved the system forward, the industry forward. So feed forward, as it stands, doesn't work. Watch out, the papers on feed forward voltage mode, they're still out there. They're in the IEEE Transactions. There's no warning on them telling you, this was a good idea, but it didn't quite work. So, there's no correction system in there to catch this. Okay, so part 1 was what to measure. Part 2 was digging into loops. Part 3 was feed forward that tried to control the input filter but didn't really control it. It just ignored it. And now we're going to say, okay, can we fix this? Good question there. No one tested in the lab. I have that question myself. And sometimes when you build a filter and you look at the impedances, I don't know the answer to that, but Paxton and Kennedy, who asked that question, university, lots of simulation goes on, less hardware goes on. So I don't know why that wasn't caught at the time. Anyway, there's a solution. Solution is this. Here's the input filter, undamped. Here's a power stage with current mode control. You take the input voltage and you do some feed forward, as he called it, from input voltage to, this is a current mode, so we're going to change the command to the current. Doesn't matter, it's the same thing. But we're going to insert a minus sign here. This is a gain of -0.5 in this case. So when this voltage goes up, the control signal for the current goes up. Exact opposite of what Kelkar was trying to do with the original feed forward. Okay, what we're trying to do now, we're not trying to ignore the filter and not see it on the output because we know we can't control it. We're treating the filter as a feedback system. So the right way to design this is the first thing you do is you do a sweep and you look at the control voltage to capacitor transfer function. So we're checking the transfer function from control to the input capacitor, and then we design a loop around it. And to make it negative feedback, we have to change the polarity here. So what we've done is we flipped the polarity. When the input voltage goes up, the error signal goes up. So that's obviously, feedback. If this capacitor is starting to ring and is going high, you don't want to pull less current out of it because it's going to push it higher. So if that capacitor current is going high, then you've got to pull more current out of it. So now we're trying to control this. And of course, at the same time, we're trying to control this. Everything is a fourth order system. So it's getting fairly complex in the system. This is exact opposite to the feed forward technique that Kelkar was trying to use. Okay, and he's almost there. Lots of pages, lots of math. We just needed to flip the side. Now, I spent many years thinking about this. Finally came up with this idea. I know I'm not the first because at least one person on our group, I think it was Colin Tuck, said, yeah, you just do feed forward with the sign inverted. So other people have done this in the past. Tends to be high power people where you can't change the filter. You got what you got. It may just be parasitics of the line. So, the people have thought about this. I don't know if they thought about it to the extent I have and built models and done optimization, but it's an interesting system now. So I've got a second order system here, the LC, second order system here. Got one control variable, which is controlling the current. We've got the feedback states to deal with. And then we've got to decide how are we going to design the system properly. And here it is, running the simulation here. So, which file is that? Let's do that live here. And let's pull up file. Spice files. Okay, so now we built two circuits side by side. So this one here is just a buck converter with an undamped input filter and no attempt to control it, but it's current mode. This one here is the undamped input filter, same current mode circuit, and then applying some feedback from this point to the control voltage. So it's got a gain of 2. Okay, so there's a -2 here, then an inverting amplifier. So, you know, we get negative feedback from this point in the system. So I just decided let's just run the two circuits side by side and then look at what happens. Let's see if we can get that. So here's the output voltage of this circuit, and then here's the filter rail for that circuit. So you can see that filter rail is starting to ring, and nothing is controlling it. But on the output voltage, I'm not seeing it yet because this is not big enough yet. Okay, so the lowest circuit here, where I haven't put any feedback around it, you know, it looks stable until it's going to get to an amplitude where it's not going to be stable. Now let's look at the other circuit here. So this is the input rail on the circuit with feedback from the filter. So the green follows the blue until the second converter here is now controlling the rail. So it's locking it in, it's controlled it. So this one's growing in amplitude. It's going to show up at the output voltage when it gets a bit bigger. And by the way, this is not a slow LT Spice model. I've mentioned this before in our webinars. WebEx, our go-to webinar, really slows down everything else that's going on in the system. While that's going on, let's look at the output voltage of the controlling converter, which is right there. And you can see that. So the red is the converter that's got no feedback on the filter. And then the yellow is the one that during this region here, it's starting to grab the input line and control it and forcing this down to a controlled value. All right, and now pretty soon, there you go. So now we start seeing the red one reacting to these big oscillations on the input filter. Okay. So, a lot going on here. This is pretty complex. I get excited about this because I say nothing's happened in filter land for 50 years that anybody's published, but now we got something going on. We are controlling this filter, and we're controlling the output of the power supply, and we're getting a pretty good response everywhere. So we've taken something that, you know, Middlebrook says was uncontrollable, and we've made this system quite controllable now. There's some compromises we're going to see in a little bit. You can see here during startup, there's a little bit more overshoot, and, you know, but the rest of the way, you know, this system is really working quite nicely, better than I expected it to. So I remember calling Dr. Volparian when we came up with this. I said, hey, Vache, guess what? You remember that feed-forward system? All you have to do is change the sign and it works. It always worked. It's just the sign was wrong. And now, you know, we got the system where we control it. And you know, this is an interesting topic now. You know, buck converters are not very interesting since 1970s because they've been solved. But now we're reaching outside the buck converter to control the filter on the input. We're not just trying to control itself. And this is what people in high power fields, they do this quite a bit. They have these source impedances. You have to control more than just your converter. You're using the converter to control the system outside what you're doing. So the LT Spice is still running, but these are the results here. Okay, so it's nicely controlled. So here's the filter with feedback. Here's the filter with no feedback. With no feedback, of course, the whole thing is oscillating like crazy. The red one is a nice, looks like a ruggedly stable system. How are we going to optimize this? Okay, Well, at this point in my career, I'm done writing equations and optimization and Lagrange multipliers and all that stuff. That's for the students out there. All right, this is a fascinating problem to control. For me, I looked at the transfer function, I looked at the control to capacitor voltage. I said, okay, that looks like it just needs some gain and it needs a pole in there. That's what we're achieving with this network. It's getting flat gain, 20K 15 nano, working with 20K 15 nano. That's a gain of 1. Here's a roll-off. We didn't put a lead there, so we're just getting a roll-off there. So if you look, there's another transfer function I'm not showing here, which is the control to capacitor voltage, which shows why this works. But if somebody wants to take this as a problem, find out the optimal compensation, find out the optimal gain, go ahead, do that. It'll be great. What I did here was I let LT Spice do the hard work for me these days. So I just changed this gain from 0.25, 0.5, 1, 2, 5, 10, just to see what happens. So it's an interesting result. I don't know what's going on here. This wiggling here is it's trying to get a hold of that input filter. This does not indicate that there's a phase margin issue. It's just there's some very large ringing on the filter, and now we're grabbing that, putting in. So during this region here, there's a lot of large signal effects coming in that give this kind of bouncing back and forth. But you can see they all look pretty ruggedly stable. When we got to a gain of 10, something went wrong and didn't regulate properly. I never got to the bottom of that because we didn't get this last part done until recently. So I don't know how many students we've got. I don't know how many students we've got looking for topics. This is a good topic. You can write a PhD dissertation on this. You can draw the curves, you can do the transfer functions, but you can also, of course, do immeasurable amounts of math to make it look like a good PhD dissertation. But this is an important topic to look into, I think. For me, the gain of 2 feels right. So there you go. How rugged is it? What if that filter changes? Well, here we took the filter inductor from 20 microhenries all the way up to 200 microhenries. And they all worked. The 200 microhenry took a little longer to settle down, but you really wouldn't expect a 10 to 1 to be that solid. So it actually worked a lot better than I expected. I only did this simulation 2 days ago, where I just swept the filter value. I didn't change any of the compensation values. Okay, so they all worked and worked quite nicely. So this is going to happen. If you have a large power systems, 100 kilowatt power system, what's in front of you, it's all over the place. You have different sources, you have transformers, you have variacs, you have line cables and so on. It's going to be quite changeable. So a lot of the the work that could go into this is how rugged is it to the change in the filter. What if I've got a 2-stage filter, a 3-stage filter? How much can this change? So there's just an immeasurable amount of simulations that you can do here, and analysis on this to try and do something different that would help the industry. Now, when we look at the loop of this system, it's interesting that you have to cross the loop. This is the outer loop gain now of current mode. So this is the trade-off. You got to cross it over before you hit that filter glitch. Okay, I can't have this loop crossing over out here because I have way too much phase delay in the system. So that's the trade-off. You got to back off a little bit on the loop gain. So when can you do this? Well, if you're doing a battery charger, who cares what the loop gain is? You just want to control the current, which we're doing very well. No one's trying to regulate the voltage very aggressively. Okay, so for that kind of system, it's fine. Would it be good for point of load converters? Probably not, because you're looking for bandwidth there. So this system's where this is going to work. If you're doing current charging systems, it's going to work. If you've got solar arrays, it's going to work. And it takes out all that variability of the input filter, which is what they were trying. Dr. Kelkar was trying to do all those years ago. So much work that can be done here. Here's a question. This one I only came up with last night, actually. It's like, oh, we've done that. We've controlled this filter. I wonder if I can hang another converter on the filter and do nothing on the second converter. Will this work if I add another power supply to the system? So if you have a multi-phase system or multiple power supplies all running from the same filter, I use one of the power supplies to control the input filter. Can I then put another power supply on there and keep it working? Like, that's an interesting approach. So again, I tried that last night for the first time and put it in your notes because it worked. Analysis of it, students out there, if you can analyze this, don't go down the rabbit hole of hardcore brute force analysis. This is an 11th order system, okay? But analysis does not have to be hard. All you got to do is look at Middlebrook's criteria again. You know, he wasn't just talking about filters, he was talking about impedances in general. But let's look at the simulation first. So here we've got two power supplies running. Red and the blue is the output voltage. This is the input filter, one input filter. So the red one here is responding to these large signal swings, and it's grabbing a hold of the control of the filter, bringing it into regulation. And then the blue one is the one that's not trying to control the filter. That responds as if there were no filter there at all. So it's perfectly good. So you can use multiple power supplies here. One of them can just take care of the filter. Maybe that one doesn't need to be tightly, you know, fast responding, and then the other ones can all run from the same line. So that was interesting. And I didn't need to run the simulation to know if that was going to work. All you need to do is go apply a little bit of Middlebrook. Here's the buck converter. This is Warparian's switch model. Actually, it's my current mode model added to his switch model. Here's the feedback through this new network. It's opposite sign to what Kelcar did. And now I just take our little emulator of measuring things. We have a Ridley box /AP310 in LT Spice. So you just hook it up to whatever you want to measure. This is how we measure impedances. You just put a big cap in there, little 1 ohm resistor, and then you run the sweep and you measure the voltage divided by the current here. And we can measure the impedance of this filter now with the control circuit in place. All right, so again, I'm just looking at impedances. Can I add another power supply to this? And what Middlebrook would have said, well, if the input impedance of the power supply is higher than the output impedance of this node, everything's going to work fine. And then now we see the effect. So here was my wildly undamped input filter with no feedback. And then when we put the feedback around it, we've knocked that peak down more than 20 dB. And here's a nicely damped low output impedance point here. No problem hooking up another power supply to that node in the circuit. So that's kind of cool. What remains? Well, students or board engineers or engineers that like to crunch transfer functions, I'm not going to do any more with this, you know. I've done the fun part. I've done the transfer functions. You know, somebody will be interested. Please pick up the work here. You know, do give us a reference that you got it from here. But, you know, if I had to guess from my experience at the university, you could get about 4 PhDs out of here. So we've got any professors that have some students who are struggling to find something to work on, this will work. I do suggest you talk to me before you start going. Get a hold of our models so we can give you a start of how this is going to work. And to turn it into, you know, the PhD or a master's dissertation, just add equations, okay? That's all you need to do. Optimization would be good. You know, can you do two-stage? How far can you take this approach? But you know, I say in the world of DC to DC converters, this is not being done in the high power world. They are doing this kind of thing. They do control filters with converters. The utility industry, you know, they use converters to control the oscillations on the line. So there's a lot of work in doing that. So higher power field has done this kind of thing. So there we are. Quick sales pitch to pay for this, and I will get to your questions. So of course we run workshops. If you like this style of teaching, of course we do hardware. We got the course in June. We got 1 space left for March. So grab that quickly because it will be gone fairly soon. We do frequency response analyzers, of course, the AP and the Ridley box, which is relatively new. This is our $6,000 unit, and this is the high-end unit for aerospace companies like this one. So in here, you've got a scope, 4-channel analyzer, computer, and RidleyWorks, and injector. So that's a great bargain. RidleyWorks software, just about every curve in this presentation came out of RidleyWorks. It will generate all the LT-SPICE files for you automatically. It's a huge, huge time saver. So if you don't have that, I do suggest you get that. It's not very expensive. It will certainly help you with design. And then come to our design center on Ridley Engineering. Go to the design center, you'll find discussions of things. We're going to write more of this up as time goes along. And finally, lots of you don't like Facebook, but Facebook is where it's happening for power supplies. We've got 6,300 members there. We talk about this kind of issue, and we have a lot of discussions about this going on all the time. So come join our Facebook. And when you download the PDF, all of these slides here, all of these things have links, so you can click right through to the link. And now that's it. I'm done with this. I got through in time. It was very, very fast. If I were to do this conscientiously, it would have been 3 hours. To cover everything that we did. I would have had a lot more, equations, a lot more measurements in here. I especially like this last part of the system here where we're getting two converters together. So lots and lots of work can be done. Endless work on this that really I think will be quite useful. Okay, let me look at some questions here. Someone said thanks. Yes, thank you all for attending. Those of you, I know some of you will drop off now at this point, but thanks everyone for coming. You will all get a copy of the recording for this. The slides are available. If you go to handouts, you can download the slides. Okay, and then you can also look at RidleyWorks and look at how that will help you generate all these transfer functions for you and all of these models. So I do encourage you to download those. So reverse polarity shouldn't make any difference. Sure, the input filter, well, the input filter is driven by a voltage source, either AC or DC. So when you're measuring the output impedance of the filter, it's with a voltage source on the input. We're not going to apply voltage, so you put a short there. If you don't do that, you'll get a very, very different transfer function. Reverse polarity diode, I don't know what that means. Yeah, some people do that. I mean, all these things get complicated by the real systems. Do you have a bridge rectifier in front of your converter between the filter and the power supply? And then you've got two separate states. So part of the filter is connected to another part of the filter when the diodes are connecting, and then they're disconnected. So it gets more complicated when you do that. But normally we look at the diodes in their conducting region and analyze the filter in that part. All right, V squared. V is, when I did V squared over P, so if you take a power supply, you want its input impedance, it's the input voltage of the power supply, the minimum value divided by the power level. And that power level should be modified by the efficiency of the converter. And it's a P max, the maximum power, because that will give you the lowest input impedance. So you have to do overcurrent, find out where it's really going to go up to before you apply this. Okay, for calculation of power supply input impedance, what do you use for V? Well, you're going to turn it to DC first. So you've got to look at, the range of DC that you're going to use. We're not sure. I shorted the input filter, got that. All right, capacitors can be voltage dependent. Yeah, they can. So if you like, you can take the input filter and apply a DC voltage to it, and then measure the filter again. Is it going to move strongly? I don't know. The multi-layer ceramic caps, what do they move? They lose about 60% of their capacitance. If you're that close, you're in trouble anyway. But yeah, you could apply DC voltage if you like and get a measurement. So spend a little more time doing the measurement. But measuring the filter is the one hardcore measurement that you do have to make in there. All right, if the input source is another DC to DC converter, same rule. Okay, DC to, remember Middlebrook did this whole thing. It's impedances talking to impedances. So you look at the upstream filters and converters, measure the output impedance of the converter. Okay, so we have an attachment for that to use with our analyzers. Okay, so you look at the output impedance of one converter, it's got to be less than the input impedance of the next converter. That's done. That's done. Do we have left half plane poles in slide 19? Ooh, long way to go back. Sure, you have left half plane poles, but not right half plane. 19. Yeah, this is just a regular left half plane pole. That's okay. Right half plane poles that we worry about. Right, so I'm remember now, I'm not calling this V in feed forward, it's feedback. And yes, of course, it works for boost, for LLC, for any topology you can think of. You've got to take care of this filter impedance interaction. Multiple crossings, well, it's a bit out of topic here, so I'm not going to cover that one. But yeah, it's the last crossing that counts, or the highest frequency crossing that counts. And Bodie touched on that too. It's a small signal issue, somebody else. Middlebrook theory about interaction of, no, it applies to any regulator. So his filter interaction with the power supply, it's anything that regulates. So it's anything with a negative input impedance. What does that mean? As the input source goes up, the current goes down. That's negative impedance. That's what causes the oscillation. So any converter does that. Actuator authority problem, I don't know that one. I'll defer to you on that, Justin. Sounds like saturation of the controller, actually. What's the power supply rejection ratio with negative feedback? I don't know, it's different, but pick up models. There you go. So the next step of the analysis here. So if you were doing just a master's degree on this, you would say, okay, well, this is a neat scheme. Now let me look at this new system. So here's the large signal model. And here's our small signal model. So just take this system here. Now let's recharacterize what is the line to output transfer function. Drastically different, I'm pretty sure. What is the output impedance of the converter? Drastically different, I'm sure. What is the loop of the converter? Different, I'm sure. But you know, this is something where we made the decision, okay, we're going to compromise this converter performance, slow it down in order to get control of this node here. But everything changes. So somebody, you know, has to go take care of that. That's the next step of the work. Why would I apply feedback to current mode rather than just damping the filter? Well, damping the filter can be large components, it can be lossy, and it may be filter components that you don't have control of. So the inductance of the filter may be leakage of a transformer, or it may be impedance of a line that's feeding you. Okay, and you don't want to put multi-layer ceramics on the board and then stick a resistor in series with them, because now it's not attenuating as good as it was before. So can you damp it? Yeah, you can, of course. You could do that, add some bigger parts. But as we're pushing to high density and high efficiency, I mean, people are pushing 99% efficiency these days. You can't afford big damping networks in there. So Middlebrook and Chuck talked about the damping networks for filters and for the Chuck converter, and they had to put a capacitor in which was much bigger than the power capacitor with a filter in series, a resistor in series with it. So damping is not, it's an option, but you know, if I can control it with two little components, maybe one transistor to do this, why would I add damping components in there? I like control simulations. Oh yeah, so feedback, here's another little thing to explore. You see that this voltage source here is connected from the input voltage to ground. There's actually advantages in connecting it over there at the input voltage. So the voltage coming in is just the drop across the inductor. So in terms of implementing this little circuit, where you connect the return on the input makes a difference to the implementation. Which one's better? I don't know, but they're going to be different. So these are all the ways that this work can expand out into many different ways and try many different things and write lots of papers, and that's what getting degrees is all about, right? How does the bandwidth, the air amp implement it? Shouldn't be an issue because we're not really doing this at very high frequencies. 2 degrees of freedom. Yeah, there are 2 degrees. We can't control the output cap perfectly and the input cap perfectly. So we're making a choice. It's like, okay, at that filter resonance, I'm not going to try and control this anymore because I've already got control of it through the current. I'm going to work on controlling this first. So you've got to make a trade-off between those two. Load transient, how does it look? We did look at that shortly. It's different. I can't remember. By the way, somebody asked about, can we get the models? Well, you can all redraw these models. So here's the deal. We're going to put all these models are going to come with our next release of Ridley Works. We're going to have an input filter section. If I gave you the models now, you wouldn't have all the subcircuits. And these are all part of what goes on in Ridley Works. You wouldn't have the switches, you wouldn't have the diodes. So, if you want to get the models, get a copy of Ridley Works, and then we'll have those models available to everyone. So we put one of them is already on our Facebook group. You can go grab that model, and all you need to do is implement your own controller, switch, and FET. So you can go get that model if you want to. So we're just still thinking about how to release these because we want people to start doing this. All right. What does the hardware implementation look like? Somebody else figure it out. I'm done. This could be a diff amp. So LT makes a nice diff amp that you could hook from here to here. That would be a pretty easy way to implement it. I'm pretty sure you can do it with one FET. Since you're inverting here, you probably capacitively couple just a FET and get an inversion through the FET, but it's been a long time since I did single transistor circuits, but it's not hard to implement, I'm pretty sure. Trade-off, we got that. LT spice bus, got that. Is it applicable only to digital power supply design? Nope, none of this is digital. It's all analog, but digital can do it exactly the same. Digital would be quite happy working in this domain, but someone's got to program out problems, Running DCM, yes, you have filter instability problems because it's still a negative input impedance. So DCM, CCM doesn't make any difference to which mode you're working as long as you're regulating the converter. Peter Schmaltz says that I think it's fabulous that you can control it. Yes, I agree. I think this is fabulous. It's a lot of fun, playing with these circuits. I encourage you, come join our Facebook group, download the circuits there that is regulating 2 converters at once and controlling the input filter. Make that your starting point for diving in here. Does the multiple converter only work if the first controller is drawing more current than the second controller? I don't know. I only ran it first time last night. And then I did put a second converter on it at higher power, and it ran into some slight problems. So you might be right there. I don't know. So maybe you have to put a little feedback in both of them, but then they're both trying to control. So yeah, unknown at this point. Have I tried step load? I tried it, can't remember. Tap off the input filter inductor, works well and can start up faster. Yep, maybe. I'm sure there's other ways to do it. Another way to do it, by the way, there's a passive way to implement this. If you just put a winding on the inductor, you get that voltage minus that voltage, hook it up to this RC network. You can apply it with just a 4 or a 2 winding inductor, which you can buy from people. So that would be another approach to doing this. So that's pretty cool. Best way to damp the input filter, there's many ways to do that. So I'm not gonna try and answer that there. Can you model the input impedance? Yes, we did that. we ran it through LT Spice. If you want to write equations, yes, you can do that too, but I'm not going to do that because it's a fairly high order system when you include the control in there. Can we control emissions from the filter? I don't know the answer to that one. Did we test the feedback filter with load steps? Same question again. Yes, we did. Not sure what that is. Anyway, they're all things that you can try. Anyway, I hope I've given you all some food for thought here. Appreciate any feedback you might give us afterwards. You know, send us an email to info@ridleyengineering.com. Other topics you might want to see. Would you like to see this more in depth? Would you like to get all the files and make this a big teaching tutorial where we, you know, charge some admission to like a half-day workshop to get all this working, where you can have some hands-on as well? They're things that we're thinking about. So let us know if you'd like to see any of that. And apart from that, we've still got 427 people in the room, which is pretty darn good. So I wish you all a good day. Stay free of COVID. It's not fun. And please give me some feedback on if some of you go and try some of these things. Please let me know what you run into and what you encounter and any help that you might need to make this work. So thank you, everybody, for attending. And I wish you all a good day. Thank you. As usual, I don't remember how to stop it all. There you go.